Imagine an invisible field that fills all of space within you, me, and the void between galaxies. This field, present since the dawn of time, may be more than a cosmic backdrop. It could be a gateway, connecting our visible universe to realms beyond imagination. The universe we see is just 5% of what exists. The rest, dark matter and dark energy, remains a profound mystery. Scientists have long searched for a bridge between our world and this unseen cosmos. The answer might be woven into the very fabric of existence, the Higgs field. Our standard model of physics maps the visible universe, but tells us nothing about the dark ocean beyond. What if the very thing that gives mass to our world also links us to that darkness? The Higgs field and its particle, the Higgs boson, could be the key to unlocking the universe's greatest secrets. They challenge us to see the cosmos as a single interconnected whole. Our journey begins with this invisible architect of reality. So what exactly is the Higgs field? It's one of the most important discoveries in modern physics, but it can be a tricky concept to wrap your head around. We're going to break it down and explore what makes it so special. Think of it as a universal energy field, a fundamental aspect of reality present everywhere, always permeating all of space. It's not something that appears and disappears. It's a constant presence, like the very fabric of the cosmos. Unlike a magnetic field, which varies in strength and direction, the Higgs field's strength is remarkably constant throughout the universe. This uniformity is crucial to its function and its impact on the particles around us. It's a subtle but powerful force shaping the nature of reality. It's as fundamental as space-time itself, an intrinsic property of the universe that underpins everything we observe. It's not just another force, it's woven into the very structure of existence. Existing since the first moments after the Big Bang, the Higgs field has been a constant companion to the evolving universe. It played a critical role in shaping the cosmos as we know it, influencing the behavior of particles as the universe cooled and expanded. You can't see or touch it directly. It's an invisible, intangible presence. We can only infer its existence through its effects on other particles. But without it, stars, planets, and people wouldn't exist. The Higgs field is essential for the formation of matter and the structure of the universe. It's the reason why atoms can form, why stars can shine, and why life can emerge. Every field in physics has a corresponding particle. It's a fundamental concept in quantum field theory. These particles are the quanta, or smallest units of the field. And for the Higgs field, that particle is the Higgs boson. It's the physical manifestation of the Higgs field, a fleeting but crucial particle that helps us understand the field's properties. The Higgs boson is like a ripple, a tiny disturbance in a calm, endless ocean. The field itself? It's a temporary excitation of the Higgs field, a way for us to probe its nature and understand its interactions. Creating a Higgs boson takes immense energy, requiring conditions that mimic the early universe, which is why it took the Large Hadron Collider, the world's most powerful particle accelerator, to finally find one. The discovery of the Higgs boson was a triumph of scientific collaboration and a major step forward in our understanding of the universe. The Higgs boson is unique. It stands apart from other fundamental particles due to its specific properties. It has no electric charge, meaning it doesn't interact with electromagnetic forces. This neutrality is a key characteristic that sets it apart. And no spin, a quantum mechanical property that describes a particle's intrinsic angular momentum. Most particles have spin, but the Higgs boson is an exception, making it a scalar particle, a type of particle that is described by a single number or scalar value, rather than a vector or tensor. Its lack of spin means it provides a uniform background for the universe, a constant and unchanging presence that influences the behavior of other particles. The Higgs field answers a fundamental question that has puzzled physicists for decades. Why do things have mass? Where does mass come from? Before its theory, physics simply couldn't explain this fundamental property of matter. The standard model of particle physics was incomplete without it. Why some particles, like electrons and quarks, are heavy, while others, like photons, are massless and travel at the speed of light. The Higgs field fills that gap in our understanding, providing a mechanism for particles to acquire mass, giving mass to fundamental particles through their interaction with the field. The stronger the interaction, the heavier the particle, and ultimately allowing the universe's complexity to emerge. Without mass, atoms couldn't form, and the universe would be a very different place. Without it, reality as we know it would be unrecognizable. The Higgs field is a cornerstone of our understanding of the universe, and its discovery has opened up new avenues of research and exploration. How does the Higgs field, this mysterious entity that permeates all of space, give particles mass? It's a question that has puzzled physicists for decades, leading to groundbreaking experiments and theoretical breakthroughs. Picture the Higgs field as a thick, invisible syrup, a cosmic molasses filling every nook and cranny of space. Imagine it's always there, an omnipresent background. Some particles, like photons, the fundamental units of light, pass through this syrup untouched, unaffected by its stickiness. Because they don't interact with the Higgs field, they remain massless and are able to travel at the ultimate speed limit, light speed. They zip through the universe without resistance. Others, like electrons and quarks, the building blocks of matter within atoms, interact with the Higgs field and get stuck, experiencing resistance as they move through it, thus gaining mass. It's like wading through a pool of treacle. The stronger the interaction with the Higgs field, the more they get bogged down, and the heavier the particle becomes. It's analogous to the difference between wading through thick mud versus easily moving through water. The mud offers more resistance, making it harder to move. This interaction strength is described by a term called the Yukawa coupling. The Yukawa coupling is a number, a fundamental constant, that precisely quantifies how strongly a particular particle interacts with the Higgs field. The mass of a particle is then simply determined by its Yukawa coupling multiplied by the overall strength of the Higgs field itself. The somewhat sensational term, God particle, though disliked by many physicists, highlights the Higgs boson's absolutely central and fundamental role in this cosmic mechanism of mass generation. Its discovery at the Large Hadron Collider confirmed the existence of the Higgs field and validated the mass-giving process. Without the Higgs field permeating the universe, all particles would be massless, zipping around at the speed of light. Without mass, atoms couldn't form stable structures, molecules wouldn't bind together, and life as we know it simply wouldn't exist. The Higgs field, therefore, allowed the initially hot and energetic universe to cool down and congeal, ultimately leading to the formation of stars, galaxies, planets, and eventually us. It's the fundamental reason why we have substance, why we can touch and feel the world around us. The underlying mathematics that describe the Higgs field are remarkably elegant and concise. But the core idea, the fundamental principle, is surprisingly simple and intuitive. In essence, the Higgs field is what makes a reality, as we perceive it, possible. It's the silent architect, the unseen hand, shaping everything we know and experience in the universe. To truly appreciate the significance of the Higgs boson, a particle that eluded scientists for decades, we need to first understand its place within its theoretical home, the Standard Model of Particle Physics. This framework is the bedrock of our understanding of the universe at its most fundamental level. The Standard Model is essentially our recipe book for the universe, a comprehensive guide meticulously listing all the known elementary particles that constitute matter and the forces that govern their interactions. It's a testament to human ingenuity and our relentless pursuit of knowledge. Within this model, matter particles, quarks and leptons, are the fundamental building blocks of absolutely everything we see around us, from the smallest atom to the largest galaxy. They are the essence of existence. Then we have the force-carrying particles, bosons, which govern the fundamental forces that shape the universe and dictate how these matter particles interact with each other. We have photons for electromagnetism, the force responsible for light and all electromagnetic phenomena, gluons for the strong force, which binds quarks together within protons and neutrons, holding the atomic nucleus together, and W and Z bosons for the weak force, responsible for radioactive decay and certain types of nuclear fusion. For decades, the Standard Model worked beautifully, accurately predicting the outcomes of countless experiments and solidifying its place as a cornerstone of modern physics. But despite its successes, it had a glaring problem, a significant flaw in its design. It predicted that W and Z bosons should be massless, while experiments clearly demonstrated that they possess significant mass. This discrepancy threatened the entire framework. The missing ingredient, the key to resolving this paradox, was the Higgs mechanism. Back in the 1960s, a group of brilliant physicists proposed the existence of the Higgs field, a theoretical field that permeates all of space and could give mass to the W and Z bosons while elegantly leaving the photon massless, consistent with experimental observations. This elegant solution beautifully patched the Standard Model, resolving a major inconsistency and provided a compelling explanation for how all fundamental particles acquire mass through their interaction with this ubiquitous field. But for nearly 50 years, the Higgs boson, the particle associated with the Higgs field, remained stubbornly unproven, a ghost in the machine, a theoretical construct that had yet to be directly observed. The search for this elusive particle became one of science's greatest quests, a global endeavor pushing the boundaries of human knowledge and technological capabilities. The discovery of the Higgs mechanism would complete the Standard Model, solidifying its place as the most accurate description of the fundamental laws of nature. But only if the Higgs boson, the physical manifestation of the field, could be definitively found and its properties confirmed. That groundbreaking discovery would change everything we know about the universe and our place within it, ushering in a new era of physics. Finding the Higgs boson was one of science's greatest challenges. The Higgs is heavy and decays almost instantly, leaving only a fleeting signature. Detecting it was like searching for a unique grain of sand on all the world's beaches. The Large Hadron Collider, LHC at CERN, was built for this epic hunt. Two beams of protons, accelerated to near light speed, collide inside massive detectors, recreating conditions just after the Big Bang. Billions of collisions happen every second, producing showers of particles. Physicists sifted through mountains of data, searching for the Higgs' telltale decay patterns. On July 4, 2012, CERN announced the discovery of a new particle matching the Higgs boson's predicted mass. The missing piece of the Standard Model was found. It was a triumph of human ingenuity, confirming a 50-year-old theory. The door to new physics was now open. The Higgs boson's discovery was a triumph, but it raised deeper questions. The Standard Model explains only 5% of the universe, ordinary matter and energy. It says nothing about dark matter or dark energy, which make up the rest. For years, the visible world and the dark sector seemed separate. But what if the Higgs boson is our portal, a bridge between our world and the dark sector? The Higgs Portal hypothesis suggests the Higgs could mediate interactions with dark matter. If dark matter also interacts with the Higgs field, it might get its mass the same way. The Higgs could decay into invisible dark matter particles, offering a new way to search for them. The portal might already be open, waiting for us to find it. Higgs portal theories explore the idea that the Higgs boson connects our universe to the dark sector. Imagine two rooms, one lit, one dark, separated by a door, the Higgs portal. This interaction could be a new fifth force of nature. At the LHC, scientists look for Higgs bosons decaying into invisible particles, potential dark matter. If the Higgs disappears more often than expected, it could be evidence of this hidden world. Higgs portal models might also solve the hierarchy problem, explaining why the Higgs mass is what it is. New particles from the dark sector could stabilize the Higgs mass. These are testable ideas. By studying the Higgs with precision, we can search for deviations from the Standard Model. If we find dark matter matching Higgs portal predictions, it would revolutionize physics. The Higgs could truly be our bridge to the dark universe. Despite its discovery, the Higgs boson leaves us with profound mysteries. Why is its mass so precisely tuned? The Standard Model doesn't predict it. The Higgs field gives mass to fundamental particles, but not all mass. Most of your body's mass comes from the strong force binding quarks. Neutrinos have mass, but we don't know if it comes from the Higgs or something else. Dark energy, the force accelerating the universe's expansion, might be linked to the Higgs field's vacuum energy, but calculations don't match observations. The connection to dark matter remains elusive. Is the Higgs truly the portal, or is the dark sector isolated? Could there be a dark Higgs boson, or a whole family of new particles? The Higgs we found may be just the tip of the iceberg. The journey to understand mass, dark matter, and the universe's fate is far from over. The next discoveries may change everything. We stand at a turning point in science. The Standard Model explains 5% of the universe. The Higgs boson sits at its heart, pointing toward the unknown. Next generation experiments will probe the Higgs more deeply than ever. A single discovery, like the Higgs decaying into invisible particles, could rewrite our understanding of reality. It would be the first evidence of physics beyond the standard model, opening the door to the dark universe. This is the grand adventure of modern physics, to understand our place in the cosmos. The Higgs boson story is a testament to human curiosity and collaboration. Thousands built the machine to find it. The next generation will decode its secrets. The universe may not make sense easily, but we are daring to listen. Will the Higgs be a simple particle, or our gateway to new realms? The next chapter is waiting to be written, and you're here to witness it. Stay curious.